This is going to be the first in a series of videos I'm making on the recap of GCSE trigonometry, leading into the latest part of the A-level course that we're covering on the same topic. So to start with, we're going to go through in this video the definitions of the main trigonometric functions. We're then going to look at them applied to the unit circle, and then we're going to look at their graphs and have a look at some of their symmetries as well. So to start with, in the first instance that you'd have seen trigonometry, it would have been in the case of looking at right-angled triangles. So I've got one drawn here as a little starter exercise, and I'd firstly like you to find the value of these 7 things here. That's sine of theta, cos of theta, tan of theta, and then using the same diagram, sine of 90 degrees minus theta, cos of 90 minus theta, tan of 90 minus theta, and then finally theta itself. So if you want to draw the picture in, pause the video, and then in a few moments I'll go through the answers to the first part of the task. Okay, so let's look at how we can figure some of these things out. We need to firstly recall the definitions of these top 3 in order to work them out, so it might be worth us writing these down first of all. So if we recall, these are to do with the ratios of sides on this right-angled triangle. Sine theta is the opposite over the hypotenuse. I'm going to label those in the picture in a moment. Cos of theta is the adjacent side over the hypotenuse, and tan of theta is the opposite over adjacent. Many of you would have learnt this using the word SOH katoa to figure out which of the 3 you're using. Now let's put these sides labelled onto our diagram, shall we? So our angle that we're interested in is here. This is our theta, so this is going to be the opposite side. 12 is the shorter leg, this is going to be the adjacent side. And obviously the hypotenuse opposite the 90 degrees is going to be here. Okay, so in order to do all 3 of these calculations, it's going to be worth us figuring out what this hypotenuse is. And that's easily done using Pythagoras' theorem, so I'm going to use these sides to do that. So this is going to be the square root of 12 squared plus 5 squared, which is the square root of 169, which is 13. Okay, so now we know all 3 sides, so we can work all 3 of these things out first of all. So that means that sine theta is going to be 5 over 13. Cos of theta, the adjacent of hypotenuse, is 12 over 13. And tan of theta is opposite over adjacent, that's 5 over 12. Okay, great. Now if we're to do these 3, this is to do with sine of 90 minus theta. You probably recognise that 90 minus theta is the angle that goes up here. And that's because in the triangle that we've got, all 3 angles add up to 180, and you've already got 90 taken up here, so these 2 add up to 90. Right, so if we think about these definitions, we've got sine of this pink angle here is going to be opposite to this one, which is 12, over the hypotenuse, which is 12/13. But you'll notice that that's the same as cos of theta, so that's going to be equal to that. Okay, so we've got a nice definition that links sine with cos over there. In the same way, cos of 90 minus theta is the adjacent to it, which is 5 over the hypotenuse 13, so that's 5/13. But that's nothing other than sine theta. And then tan of our new angle here is opposite 12 over adjacent 5, that's 12/5. But you'll notice that that's 1 over tan of theta on its own, so we can put that as well. Okay, so now we've got those 3 done, we can then use any of the above to work out the value of theta. I'm going to use tan of theta to do this because those were the 2 sides that we got in the setup of the question. So if I write down what I'm going to do here, so if tan of theta is 5/12, then you can use the inverse tan button to work out the angle inside, and that's going to give you this. And if I've got my calculator in degrees, then I can do inverse tan of 5/12, and that's going to give me 22.6 degrees to 1 decimal place. Okay, so if we generalise what we've done here, we've got some nice kind of starting off definitions to write down. So firstly, these 3 are the main definitions that we've used for sine, cos, and tan. I'm going to write their full names as well, so we know what these things are short for. This is called sine, this one's called cosine, and this one's called tangent. Okay, it's worth noting as well that the two angles that we've got in this triangle here, these two acute angles, are what we call complementary angles. Okay, that means angles that add up to 90 degrees. And that's where this co comes in into our definitions here. So cosine really means complementary sine, which means it's the sine of the complementary angle. And we saw that over here when we did this one. Cos of 90 minus theta is sine of its complementary angle. So that's the reason why we named them that way. Okay. All right, I think that's probably a good thing to get us started off with. If you want to write down these three definitions as well as separate rules, then you can do. So that's using trigonometry in a right angle triangle. But in order to extend our ideas of trigonometry beyond just using small angles like this, we tend to want to extend our thinking into using these functions on a circle. And in fact, trigonometry, the trigonometric functions are sometimes called circular functions because they are more to do with circles than they are to do with right angle triangles. So I'm going to move on to a new page. We're going to set up a circle diagram instead, and we're going to relate sine, cos, and tan to that picture. Okay, so I'm going to start by setting up some axes. If you're going to draw this, you might want to draw it nice and large so we can put lots of things on the diagram. And then I'm also going to draw what we call the unit circle on these axes, which is a circle at the origin, as best I possibly can. Maybe I'll try that again, make it a little bit of a better circle. Let's go. Okay, it's probably as good as it's going to get today. Okay, so this is the unit circle, and it's called that because we're going to give this circle radius 1, which means that it's going to go through 1 on the x-axis here, 1 on the y-axis here, and then -1 here and -1 here. Okay, so now what we're going to do is we're going to try and get a diagram that involves the three trig functions that we've looked at already, and we're going to extend it to include any possible angle that we like. So what we're going to do is, the convention is to start here at 1, 0, and then rotate anti-clockwise around an angle this way. So my angle is going to start here and go that way, and it's going to end up with a point up here. This is going to be some point on the circle. Let's call the point P. It's got an x-coordinate and a y-coordinate. And what we can then do is join it to the origin to make what we call a ray like this. So I'm going to join here to here. And then what that can also do is give me a right angled triangle that gives me the x and y coordinates on its legs. So let's put that on as well. So we've got x coordinate here, and then the y coordinate goes up the side here. Great. Okay, so the angle that we've turned through anti-clockwise is going to go in here. This is what I'm going to call theta. And then because we're on the unit circle, the hypotenuse, wherever it happens to go, I can put it in any of these four quadrants, is always going to be 1. So that's my picture over there. Right, now using the definitions that we've looked at before, we can work out what x and y are in terms of the trigonometric functions. So maybe let's draw this triangle again. Okay, so if we recall then that sine of theta, where theta is the angle in here, is the opposite side, which is y, divided by the hypotenuse side, which is just 1. So that's going to give me that sine theta equals y, which is the y coordinate that we're at. And in the same way, cos of theta is the adjacent side x over the hypotenuse side 1, which is again just the x coordinate on its own. Okay, so by rotating around this circle, it seems that no matter where we go, we can define the x-coordinate as cos of theta and the y-coordinate as sine of theta. And then that gives us a way of finding these things for any angle that we like. So if we go this way, that's going to give me negative angles. For example, if I want to go find sine and cos of negative 30 degrees, I can go 30 degrees down this way, draw another ray, and then my x and y coordinate will give me the cos and sine values of minus 30. Okay, so let's add that to our coordinate point. So this point we've got here is the same as cos of theta for x, and then sine of theta for y. Okay, and then clearly, if I was to go 360 degrees around the circle, past where I've got to already, these values are going to have the same amount. And that's where the repetition comes in terms of 360 degrees. Okay, so there's lots of symmetry in this picture. I think the best thing to do now is to use this picture to draw the graphs of sine, cos, and tan. We already know where sine and cos comes from on this picture, so I think it's worth us doing tan theta as well. So tan theta is defined as the opposite side divided by the adjacent side, but that's just y over x. Let me just change colour. Okay. And then again, if we use the definition up here, y is cos of theta. No, it's not, sorry, y is sine of theta. And x is cos of theta. So we get a nice identity here that links sine and cos and tan together. Okay. In fact, this is often taken as the definition of tan theta, in that it's sine theta over cos theta. But in terms of the geometry then, the idea behind tan theta is that it's the height of this right angled triangle divided by its width, which gives us the gradient of the hypotenuse. So that's quite a useful thing to think about. If you know what angle you've got, then you can measure the gradient of the hypotenuse, and that's the value of tan theta. That's quite a nice thing to think about. Okay, so let's use what we've done now to get the graphs of these functions. As I start here at my angle of 0, I can then rotate around anti-clockwise, and as I go round, I can plot the values of cos, sine, and then we'll do tan as well. So starting off with sine theta, there's a GeoGebra that I found that kind of plots these quite nicely. So here we are, starting at theta equals 0. If I move around, remember that sine theta is the y-coordinate, which means that we're plotting the height on the circle as you go round. So let's write that first of all. Okay, so as I raise my angle up, away from 0, we're going to go around this way. So sine theta will start at 0, that's the height. As we move through the first quadrant, sine of theta is getting bigger until we get to 1. That's at theta equals 90 degrees. Then as I go around into the second quadrant, we're going to move down. The height is getting smaller, and it's going to go back down to 0. And that's with theta being 180 degrees. We're going to continue around to 270. That means that sine theta is moving negative because the y-coordinates are negative. At 270 degrees, sine of 270 equals minus 1. And then moving back round in the fourth quadrant, we're moving back up towards 0 from the negative side. And then sine of 360 degrees gets us back to this beginning of the cycle, which is 0 again. Okay, so you're going to want to draw that picture in, and we'll make a note of some of its properties. What you've got to also imagine is that this angle can move around as many times as I like. I can now continue past 360 degrees to get round to 720 and continue. I can also start again at 0 and go backwards and get all the negative angles by moving around clockwise. Okay, let's make a list of some of the properties of the sine graph then. So the first thing that we should probably notice is we should make a note of what the roots are. So this graph has roots, and these roots appear frequently, but how frequently? Well, they appear at every multiple of 180 degrees. If you imagine the graph continuing in both directions, then you're going to get every multiple of 180 degrees will give you a root. So I'm going to say theta equals, and I'll write it this way, I'll do 180 degrees times n, where n is an integer. Okay, so I'm going to use some algebra to refer to multiples of a certain angle in order to describe these things. Okay, it's also got maxima. Every so often this is going to reach its maximum height, and we can describe where those are going to occur as well. Okay, so the first time we get a maxima in the positive angles is going to be 90 degrees. But then to get all the way around to the next maxima, it's going to take a further 360 degrees. And that's going to be in both directions. It's going to be adding and subtracting multiples of 360. So I can describe that by saying 90 degrees plus 360 degrees times n. Again, n is an integer. So again, I can make n negative in order to go back to the negative angles, but this will get me all of the possible maxima on the graph. The minima, it's got plenty of minimum values as well. And we can certainly describe those as well in a similar way. The first one we get to is at 270. And then each one past and before that is going to be a multiple of 360 away. So we can describe it that way. Okay, and then also there are some lines of symmetry as well that we can use. So every so often we get some lines of symmetry that has the same either side. So the first of which is going to be here. Because when you reflect an angle in this line, then the value of sine is going to be the same, as you can see. If I go forwards 20 degrees that way, the value of sine will be the same as if I go 20 degrees that way. The second one is here. We can put that in as well. And it works the same way. So let's describe these. Well, these are a little bit closer together. These are 180 apart. Starting at the first one, which is at 90 degrees. So that's 90 degrees plus multiples of 180, again using 180 times n. Okay, now there's a couple more properties I want to refer to which are really useful in exploiting the symmetry of this graph. So let's think about what happens when I go backwards along this graph into the negative angles. It's going to go back down this way. I'm going to do this roughly speaking, and back up to 0, and then it's going to go back up this way and back down that way. Let's draw it roughly speaking like that. So I want to think about what happens when you make an angle negative. If I was to have some angle here, and I take the value of sine, then that's going to be some kind of positive number here. I think roughly about 0.7 based on what I've drawn. If you then go to the negative side and go to negative theta, I want to think about what happened to the value of sine in this case. So what's going to happen is it's going to go down to this part of the function here and then across this way. Okay? And if I've drawn this accurately, what should happen is that the value of sine should swap its sign, if you like. So there's a property we can write down, which is this. Sine of negative theta is going to have the negative value of sine of positive theta. So that's how we can write this property like this. So in other words, you can effectively factor out, in quotes, a minus sign from the argument in here. Okay, and what this means is that the sine function is what we call an odd function. Okay, any function at all that has this property of taking out the minus sign like this, with this kind of idea of reflecting across and then reflecting down as well, is called an odd function. Excellent. I can maybe do an example of this so we can see a proper example. So if I want to do sine of minus 40 degrees, well, that's just the same as sine of 40 degrees. Okay, you can replace theta with any angle there. Okay, I think finally we should talk about the period of repetition on this graph. So, and also I guess as well how high and low the function gets, the kind of range of the function, if you like. So the period of the function is the amount of time, I guess, or the length of the x-axis that you've got that gives you one cycle of the function, and that's 360 degrees. Okay, so that's length of a single cycle. Okay, if you which means then if you add 360 degrees to your angle, that's going to give you the same value back again because you've gone through a full turn of your cycle there. Okay, and then also let's write down what values sine theta can be in between, and that's going to be between -1 and 1 height-wise. Okay, so we've pretty much fully described a lot of the properties of the sine graph there. If you want to do the same with the cos graph and try and get all the same information, if you could pause the video and draw a sketch yourself, and then I'm going to go through it in a moment's time. Bearing in mind as well that the cos graph is plotting the x coordinates, again, as you start here and then rotate around the circle around this way. Okay, hopefully you've had a chance to think about the same kind of information for the cos graph. I'm going to do the same again now. So here's my cos graph, again using the unit circle. We're starting at theta equals 0, and we're this time plotting the x coordinate as we go around, the width if you like. Okay, so starting at 0 for the angle, the value of cos is going to be 1 because that's my x coordinate. As I rotate round, the value of cos is going to decrease because the x coordinate is decreasing. So for example, at 54 degrees, that means that cos of 54 degrees is 0.588 because that's the adjacent side there. Continuing round, we get to cos of 90, which is going to give me 0 because that's the x coordinate there. It's at 0, 1. Continuing on, it goes further down. Cos is now negative because the x coordinate is negative. At 180 degrees, we're at -1. And then continuing on, it goes bigger through the negatives towards 0 again. That's at 270 degrees. Until you get all the way back to the end again, which is at 360 degrees with a cos value of 1. Okay, so this should be familiar to you, hopefully from GCSE, but that's the value of the shape of the cos graph. And again, it continues on forwards and backwards to positive and minus infinity. Okay, now let's talk about some of its properties. So what did we say first of all for sine? We had roots and then maximum minimum. Right. So the roots of this function seem to be at what looks like odd multiples of 90 degrees, right? It's got one at 90 degrees and then every 180 degrees past there. Okay, again, n is an integer. Okay, positive or negative. The maxima are going to be what look like at 0 and then 360 and then at the next one at 720 and so on. So that looks like clean multiples of 360. The minima are going to be down here at 180 and then it looks like multiples of 360 after that. Sorry, at theta equals and then 180 plus multiples of 360. Okay, what have we also got? We've also got some much nicer, I think, lines of symmetry here. We've got lines of symmetry, first of all, on the y-axis, because the function will continue down this way. You've got one here at 180, which is a very nice one, because it means that when you're reflecting here, the angles that you get add up to 360. And then here. Okay, so we've got lines of symmetry. At what look like clean multiples of 180 degrees. And now let's talk about what happens at the origin as well. What happens when we reflect our angle from positive to negative? So it's very similar to what we had before. I'll continue the function back a little bit here. If I've got an angle of theta here, if I reflect over to negative theta this side, then it appears that this time the values of cos are going to be the same. Okay, because it's entirely symmetrical about the y-axis. So if these agree, and that's going to be the case for any pair of angles like this, it looks like we can write down cos of minus theta, make that clear, is the same as just cos of positive theta. Okay, that's a really, really nice property. It means that any negatives inside this argument we can kind of ignore and then go straight to the positive version of that angle. And what this means, you probably guessed from the last example, is that cos is what we call an even function. Okay, great. Lastly then, we'll talk about the period and the amplitude as well. So the period of cos is, again, 360 degrees. We get repetitions every 360. So we can write that as cos of theta plus 360 is the same as just cos of theta again. Okay, that's adding or subtracting 360, I suppose. You can go forwards and backwards by that amount. And then again, cos goes between -1 and 1. Okay, and that's a full description of the Cos graph. Now, I'm going to stop the video here. What I'd like to do as a bit of an extra task is to do the same thing but for the value of tan. Draw me the graph, please, and then see if you can get this information for the tan graph. You won't be able to do all of them, but do as many as apply to the shape of the tan graph once you've got it. Okay, thanks, Year 12. I'll see you in the next video.